Do you want to do like an intro and stuff?
Yeah, sure. Hi everyone, welcome to this video. I know that Cambridge interviews are coming up, so I got my friend David to interview me, so this is going to happen right now and hopefully it'll be helpful. Don't take this as a perfect example, but as just like a normal example.
Yeah, and these are just questions that are similar to the ones that could come up in your Cambridge Medicine mock interviews, and also related to other, I said mock interviews.
Cambridge actual interviews.
Yeah, and it can relate to other subjects as well. Great. So Rosia, I want you to first of all take a look at this graph here, and just describe to me what you see first of all.
Okay, so I see that this graph has got something to do with norepinephrine and acetylcholine, and there's a clear distinction between something that happens before rubbing and something that happens after rubbing, and there's a different levels of response maybe to those drugs. And there's also different points along the response curve with values.
Great. And can you tell from this diagram here what the y-axis might be?
Does the 2G have something to do with it?
It does, yeah.
So potentially it could be the response level of the drugs acting.
What do you think G might mean?
G, I'm not sure.
No worries, it's to do with like grams of tension really.
Okay.
Right? And what do you think the x-axis is then?
It looks like time.
Yeah, good. And it's just shown for scale here as 5 minutes. Okay, good. And what are the differences you see before rubbing and after rubbing?
So before rubbing, there's clearly a break somewhere in the middle of tension, potentially, and then the tension goes down after an extended period of time, whereas after rubbing, the tension continues to go up after the plateau.
And in response to which drug in before rubbing does tension go up?
In response to norepinephrine before rubbing, the tension goes up.
And when does the tension go down before rubbing?
It goes down before the addition of acetylcholine.
Yeah. Are you sure it's before the addition of acetylcholine?
Oh, sorry, I meant after the addition
Cool.
of acetylcholine.
Good. And I'll just give some context to this. So this experiment was obtained from taking measurements from a rabbit aorta. And you were correct to identify the drugs. Norepinephrine, also known as noradrenaline in the UK, was applied, and as you said, tension increased. And what do we call it when tension increases within a blood vessel? You know what that
that's
term
like vasoconstriction?
Yeah, good, vasoconstriction. And what about when tension decreases in response to acetylcholine?
Vasodilatation.
Good. And just to explain what the rubbing means, so when this experiment was done by Furchgott, his technician would vary on certain days. And one technician prepared the rabbit aorta specimen differently to the other. And the way they prepared it was using a cotton swab to rub the inside just to remove any residual blood or any other residual material. And that's what after rubbing means. Whereas another technician wouldn't rub that cotton swab on the inside. So what does that tell you about the mechanism of action of acetylcholine?
It has something to do with the inside of the blood vessel, perhaps the endothelium of the blood vessel.
Yeah, good. And how do you think acetylcholine might be mediating that then?
Potentially there's receptors on the endothelium that respond to acetylcholine.
Good. And where does the decrease in tension or the vasodilation happen? Which part of the blood vessel?
Decrease in tension perhaps happens on the outmost part because it doesn't matter if the endothelium is there or not.
Yeah, true. So what would you call that layer of the blood vessel?
I can't remember.
No worries. So if we go through the layers of the blood vessel, you were right, we start with endothelium on the inside, then we have a bit of elastic tissue and so on, but the smooth muscle And it's a smooth muscle that contracts and relaxes.
Okay.
So if acetylcholine is acting at the endothelium, as you correctly said, how is it then able to cause relaxation of the smooth muscle, do you think?
Potentially there's nerve connections from the endothelium to the
That's
smooth
one
muscle.
possibility, yeah.
Or maybe it diffuses through the
Yeah.
endothelium to get to the smooth muscle.
What would diffuse do there, do you think?
Maybe an agent that's made by the endothelium that then contacts the smooth muscle.
Why can't it be the acetylcholine diffusing through, do you think?
Perhaps because acetylcholine only really can attach to the receptors, and they're too small to go through the endothelium.
And based on this graph as well, how do you know that acetylcholine can't just diffuse through to the smooth muscle to have the same effect?
Because when there's no endothelium, when it's just smooth muscle, the acetylcholine doesn't cause a decrease in tension.
Exactly. Good. As you said, the endothelium is required, and as you correctly identified, there is a diffusible component that goes from the endothelium to the smooth muscle. And if it diffuses, what does that tell you about the nature of that molecule?
It's hydrophilic.
Would it be hydrophilic? Are you sure?
Anything that diffuses, what is the nature? Well, I guess it's got to be small.
Yeah.
It's got to be able to go through cell membranes.
Yeah.
So, would that be hydrophobic?
Yeah. But the main thing, as you said, is it's small. And that's why it's actually just NO, nitrogen and oxygen bonded to each other, that causes vasodilation and relaxation of the smooth muscle. Good. I want to stick to some questions on the cardiovascular system. And can you just briefly describe to me how blood flows through the human heart, what route it takes?
So blood goes through, so for example, after oxygenation in the lungs, the blood enters via the pulmonary vein to the left atria.
Yeah.
Then it gets squeezed down to the left ventricle before it's pumped out via the aorta to the rest of the body. And then it comes back to the... This is so bad.
That's okay.
The other vein, the vena cava, vena cava,
good.
and then it gets pumped out to the lungs by the pulmonary artery.
Yeah, good. And what are the chambers on the right side of the heart then? What are they called?
They're called the right side of the heart. They're called the right atrium, right ventricle.
Yeah, good. And good. So that's the basic flow of blood throughout the heart. Now, what if I told you in some people's hearts there is a hole between the two atria? What would you expect to happen to the flow?
I think there would be some kind of turbulent flow, so like mixture of oxygenated and deoxygenated blood, especially because oxygenated blood goes to the left side of the heart, and there's deoxygenated blood on the right, so potentially blood going to the body will be a less proportion of oxygenated blood.
Good. Now, that is what happens eventually to these people, but actually when they're born with this condition, for many years, until maybe their teenage years, even to the age of 20, they don't experience many symptoms of it. And they don't have any problems with receiving oxygenated blood to the body. Why might you think that be?
Maybe because blood, like there's an increased pressure in the left side of the heart, so like normally if you had a hole, like there'd be decreased pressure on the right side, so there wouldn't be as much pressure forcing the deoxygenated blood to the oxygenated chambers.
And why is there increased pressure in the left side?
Because it needs to have more pressure to be able to pump to the rest of the body.
And if you looked at it anatomically, what would you expect to see? If you looked at, if you were comparing the left side and the right side of the heart?
The left side of the heart would be larger. It would have like thicker myocardium.
Yeah, good. So therefore you're right. the net flow early on in life is from the left to the right. So you end up with just more oxygenated blood to the lungs, which isn't a big deal. Might affect gas exchange, but good. And then, why do you think, let's say at the age of 18, 20, these people start experiencing symptoms of fatigue, breathlessness? Why might that be? What's changed?
Maybe because even though early on, like, blood flows from left to right side of the heart, maybe because of just use and wear and tear and like further, like just growing older and things in the heart not working as well, maybe the shunt reverses. And
so the shunt does reverse, you're right, but it's not for the reasons you said. What else do you think it could be?
Is it to do with something like decreasing levels of hormones or increasing levels of hormones?
That's a good idea, might have an effect, but let's think about it just in terms of pressure.
So if the shunt were to reverse, then that means that there has to be greater pressure on the deoxygenated side of the heart. So does that mean there's just more like pressure going to the lungs, like the lungs receive more? I'm not actually too sure.
So the lungs would be receiving more blood, you're right with that, but what else would be receiving more blood, do you think?
The muscles, the organs of the body.
The muscles, what else?
The brain.
Yeah. What else?
The heart itself.
Where exactly?
Like the heart muscle, like by the coronary arteries.
Right. Yeah. That's okay. No, sorry. I see what you mean. Through the coronary arteries. Okay. So originally, which way was the flow going before the shunt reversal?
Left to right.
Right. So which side is receiving more blood than usual?
The right side of the heart.
What effect would that have?
That means there's more oxygenated blood going to the lungs.
That's part of it. But what effect would that have on the heart muscle?
Right. So it means that the right side of the heart will get bigger over time.
Why is that?
Because there's more blood going into it.
So what does the heart do with that blood?
So the heart keeps on pumping it, but then it has a greater volume of blood to pump. So then it just grows because that's how muscles.
Yeah. Same reason when people go to the gym, their muscles get bigger, increased work. Same thing happens to the heart. Good. So then, can you just clarify for me why the shunt reverses then?
So because of the continual shunting of left to right over time, that causes strain on the heart muscle, which leads it to grow larger, which means that the shunt reverses so that the right side of the heart is strong enough to pump blood to the left side.
Good. I want to move on to another question now, non-medical related. And I want you to take a look at this diagram. And I'm just going to explain some of the context behind it. So during World War II, the US wanted to invest money in putting armoured plates on their planes. And they wanted to find out where is the best place to put armoured plates on these planes so that they survive and the passengers survive and so on, all the pilots and the fighters. And what they would do is every plane that would fly back from battle and land at their air bases, they would sample where all the damage was, like bullet holes for example, and they came up with this heat map here. So based on this heat map, where would you advise them to put armour on their planes?
So it looks like from this map that bullets tend to hit the edge of the wings or the very centre of the body of the plane or the tail. So I would advise putting it where there is most damage, which could potentially harm the planes flying or the people inside the plane, and that looks like the middle of the plane. Potentially, if I was to put it on the edges, they would have to be balanced because you want to keep the plane's function. Or even at the tail, you want it to be balanced as well. I think so. I would put one in the middle, couple on the wings, and a couple on the back.
What do you think about when you see that there's no damage done to the propellers of the plane?
I think that perhaps it's because like the plane itself is shooting from that direction. So, or I think maybe it's because the propellers themselves propel the bullets away. So
Maybe.
Or maybe it's just because like the propellers themselves are too strong a target to be able to be damaged by a single bullet.
So you do still get damage, in fact.
Okay.
But none of the planes that came back had damage on the propellers or where the pilot was sitting, for example. What do you think about that?
So does that mean that this experiment was taken, the heat map was drawn from the planes that came back?
Right. Yeah.
Which means that like the actual true damage that happened was to the propellers and to where the pilot was sitting.
Yeah.
Oh, I see.
So where would you put armour on this plane then?
I would put it on the propellers or where the pilot's sitting.
Yeah. Would you put it on any of the red dots?
Probably not, because clearly the plane survives if the bullet hits the red dots.
Good. Did you have any questions about that or any of the previous questions?
So I was wondering what about NO makes it a factor to be able to cause vasodilation?
So it actually binds to soluble guanylyl-cyclase, which produces cGMP, which begins a whole messenger cascade, which eventually leads to I can't remember. Eventually leads to something, and eventually causes muscle dilation.
Thank you very much.
No worries. What is the mechanism?
Don't ask me.
Let me open Anki.
Something about cGMP.
It is cGMP, yeah. I know it's guanylyl-cyclase.
Yeah.
cGMP. That doesn't help.
Look at those Anki stats, man. Shall I close the...
Oh yeah, sure.